Assalamu alaikum. Chapter number 1, Measurements, Exercise Numericals. Numerical number 1, Estimate number of heartbeats in a lifetime of 60 years. For solution of this numerical, average resting heart rate, let's say it's 80 beats per minute. Beats per hour is equal to 80 beats per minute multiplied by 60 minutes per hour. It becomes 4800 beats per hour. And for beats per day, 4800 beats per hour multiplied by 24 hours per day. Hours and hour cancel. 4800 will be multiplied by 24. It becomes 115200 beats per day. Beats per year is equal to 115200 beats per day multiplied by 365 days per year. Then it becomes 4204800 beats per year. For a lifetime of 60 years, 4204800 beats per year multiplied by 60 years. And the answer is 2522880000 beats. Numerical number 2, determine the dimensions of each of the following quantities. There are two parts. Part A, v square by ax, and part B is at square by 2. We have to determine the dimensions for these two expressions one by one. First, we will take the dimensions for expression A, v square by ax. For v square by ax, v has dimensions of lt minus 1 and it has a square on it, so we will put on square. A is acceleration and it has dimensions of lt minus 2, x is displacement with the dimensions of l. This l and l has same base and powers are 1 plus 1, so it will become l square t minus 2. In numerator there is a square. We will break down this square and it becomes l square t minus 2. Now there is l square and l square in numerator as well as in denominator, so they can be cancelled. Likewise, there is a t minus 2 dimension and t minus 2 dimension in numerator and denominator. They can also be cancelled. So this expression v square by ax is dimensionless. It has no dimensions. And it is proved. For part B, there is an expression at square by 2. A has a dimension of acceleration which is lt minus 2 and t has a dimension of time which is t square. 2 is constant. Now L t minus 2 and there is t with the same base and opposite power plus 2. 2 is constant, it will remain as it is. They become 0. So there is a dimension of L with a constant in its division or denominator 2. So the dimension is L and the whole answer of this expression is L by 2. Now there is numerical number 3. If A is equal to x square by y square z, then find the percentage uncertainty in A. The percentage uncertainty in x, y and z are 1%, 1% and 2% respectively. For this numerical, we will use this formula through the rules of uncertainty principle of power and multiplications. Percentage uncertainty in A जो हमने कैलकुलेट करनी है is equal to 2 into percentage uncertainty in x plus 2 into percentage uncertainty in y plus 2 into percentage uncertainty in z. Because there is an expression of A is equal to x square by y square z. That's why this formula holds. Because through the power rule of uncertainty, if there is a power here with some expression that is x square then this power will be multiplied with its percentage uncertainty. Likewise for y and likewise for z. So the given values for percentage uncertainty in x, y and z are 2 into 1% plus 2 into 1% plus 2 into 2%. 2 into 1% is 2% plus 2 into 1% is 2% plus 2 into 2 is 4%. 2 plus 2 4 and 4 plus 4 8. So the total uncertainty in A will be 8%. So this is numerical number 3. For numerical number 4, a spherical ball of radius r experiences a resistive force F due to the air as it moves through the air at speed v. The resistive force F is given by the expression F is equal to CRV, where C is constant. By using dimensions, derive SI base unit of the constant C. Now the given expression for this numerical is F is equal to CRV. By rearranging this formula, C is equal to F divided by RV. And for F, there is formula through Newton's second law, F is equal to MA divided by RV. Now we can write the dimensions for C. For M, mass. For acceleration, LT minus 2. For R, L. And for V, LT minus 1. Now let's solve this equation. M LT minus 2 divided by L and L square T minus 1. Now shift these values of L and T, dimensions of L and T, from denominator to numerator. MLT minus 2, L minus 2 and T plus 1. Now L1 minus 2, because bases are same, so powers can be added. It has power of 1 and it has power of minus 2. T minus 2 and plus 1. So the final answer will be M L minus 1 T minus. So the final answer for this numerical would be ML minus 1 T minus 1, and the SI unit would become for M kg, for L minus 1 per meter, and for time per second. So kg per meter per second is the SI base unit of C. Now for numerical number 5, the pressure P at the depth h in an incompressible fluid of density rho is given by P is equal to rho gh, where g is acceleration due to gravity. Check the homogeneity of this equation. To check the homogeneity of this equation, we have to check the dimensions on right hand side and on left hand side. If they are equal, then the equation is homogeneous. For pressure P, we have formula force per unit area. Let's write its dimensions. For force, we would use MA. Now MLT minus 2, and for area there is L square. Now we can use simple method of simplification. For this L minus 2 from denominator would shift at numerator and it become L minus 2. Then the formula is ML1 minus 2 T minus 2, and for right hand side we have the dimension of ML minus 1 T minus 2. We would mark it as equation 1. Now for left hand side we have equation rho gh, and for rho we have formula of mass per unit volume, and for g we have gravitation and h. Now let's write down the dimensions. M, and for g we would use LT minus 2, and for h there is dimension of L. For volume, we have dimension of L cube. Now let's simplify this formula. M, L and L would become L square T minus 2, and this L cube from denominator would shift at numerator and it become L minus 3. M L 2 minus 3 T minus 2 is equal to M L minus 1 T minus 2. Equation number 2. So from equation 1 and 2, from equation number 1 ml minus 1 t minus 2, and from equation number 2 ml minus 1 t minus 2, left hand side is equal to right hand side, hence proved. Hence proved. That means this equation is dimensionally correct. Next, there is a numerical 1.6. Estimate that how many protons are there in a bacterium. Take mass of bacterium as 10 raised to power minus 15 kg and mass of proton as 10 raised to power minus 27 kg. So most of the bacterium's mass comes from protons and neutrons, and they are roughly equal in number within the cell's nucleus. Therefore, we can estimate the total number of protons by considering this formula. Number of protons is approximately equals to mass of bacterium divided by mass of proton. According to the given values, mass of bacterium is 10 raised to power minus 15 kg approximately, divided by mass of proton is 10 raised to power minus 27 kg, which ultimately becomes 10 raised to power 12. So this is your final answer for this numerical. So there are 10 raised to power 12 protons in a bacterium. So next, for numerical number 7, we have estimate that how many hydrogen atoms does it take to stretch across the diameter of the sun. Take diameter of the sun as 10 raised to power 5 kilometers. We will break it down in meters. 10 raised to power 5 plus 10 raised to power 3, 5 plus 3, 10 raised to power 8 meters. And diameter of proton 10 raised to power minus 14 kilometers. For kilo, 10 raised to power plus 3, and minus 14 plus 3 would become 10 raised to power minus 11. We would use this formula for the solution of this numerical. Number of hydrogen atoms is approximately equals to sun's diameter divided by hydrogen atom diameter. And the approximate sun's diameter is given as 10 raised to power 5 kilometer divided by, for hydrogen we would use 10 raised to power minus 14 kilometers, and for kilometers we would use 10 raised to power 3, and 10 raised to power minus 14 multiplied by 10 raised to power 3 meters. It would become 10 raised to power 8 meters divided by 10 raised to power minus 11 meters. And the final answer is 10 raised to power 8 multiplied by 10 raised to power plus 11. The bases are same, so we can add powers. The answer is 10 raised to power 19 hydrogen atoms. So this is numerical number 1.7. Now numerical number 1.8, last numerical of this exercise is the current passing through a resistor R is equal to 13 plus minus 0.5 ohm is I, and I is current 3 plus minus 0.1 amperes. We have A, B, C and D parts. We will solve it by given data. 1.8, for part A, he asks calculate the power consumed correct to one significant figure. So for power we have formula P is equal to I square R, and we have values from given data. For I we have value of 3 and for R we have 13. So we can use 3 square multiply by 13 ohms. So it would become 117 watt. So this is the answer of first part. For part B, find the percentage uncertainty of current passing through the resistor. So the formula is percentage uncertainty of I means current, is equal to, we have value for current 3 plus minus 0.1. So this uncertainty, absolute uncertainty 0.1 would be divided by measured value, which is 3, and multiplied by 100%. 0.1 divided by 3 multiplied by 100%, and it becomes 3.3%. For part C, find the percentage uncertainty of the resistance, and the resistance absolute uncertainty is 0.5 and its measured value is 13. So we would solve it. Percentage uncertainty of R is equal to 0.5 divided by 13 multiplied by 100%. So it would become 3.84%. For last part of this numerical, find the absolute uncertainty of electrical power, and we had formula of power P is equal to I square R. So to solve this part, we have formula percentage uncertainty in power is equal to, by the rule of power we have square on I, that's why there is a power multiplied by percentage uncertainty, that is 2 into percentage uncertainty in I plus percentage uncertainty in resistance. So we would solve it by using values of 2 into 3.3%, which was percentage uncertainty of current, plus 3.84%, and the final answer would be 10.44%. And we can also convert this answer into fractional form, 117 watt with 10.44% uncertainty. And for decimal answer, we can break this percentage and it would become 117 plus minus 12.21 watt. So this is numerical number 8.